All right, so this is going to be the third and final part of the problem, the weak acid strong base titration problem from before. We've done part A, 0 milliliters of sodium hydroxide being added. We've done part B, 45 milliliters of sodium hydroxide being added, and now we're going to do part C. Part C, which should be apparent from the numbers that were given in this particular problem, is different because it's at the equivalence point. And I'm going to go through and sort of use the same problem-solving process so that if you don't see if we're at the equivalence point, you realize that, in fact, we are, and things that we need to sort of bear in mind when calculating pH at the equivalence point. As with part B, which is before the equivalence point, you can divide this up as a two-step problem. You can. You don't necessarily have to, but I'm going to for purpose so that you really see what's going on. Same two-step problem as before, where part 1 is a Bca chart and part 2 is an equilibrium problem. But the part 2, how we're doing that second problem, the equilibrium problem, is going to be different than what we did in the previous problem. And you'll see why, hopefully, when we get there. So I'm going to do the first things first, the Bca chart. And again, Bca charts are based on neutralization reactions. So we're going to write that same neutralization reaction we wrote previously. The sodium hydroxide plus the acetic acid yielding sodium acetate and water. Now we're plugging in moles. I'm not going to show the work for calculating moles of the sodium hydroxide in the acetic acid. It is based on the volume and the molarity, which we have. We know for both of those things. But you see, once you calculate moles, we have 0.005 moles of the NaOH and 0.005 moles of the acetic acid. So this tells us that we're at the equivalence point. Now the reason I'm going through the Bca chart, and while it's not totally necessary for you when you're solving these problems, is just to make you aware of sort of what's going on in your solution. Because you have the same number of moles of each, then you take the smaller one and you make it go to 0. So I'm going to subtract 0.005 from both of these things. That's going to leave me with 0 moles of sodium hydroxide and 0 moles of the acetic acid. Wow, that looks like a 5-year-old word, but it does in fact say 0 moles. In your flask at this point, you have no sodium hydroxide, excuse me, no sodium hydroxide, no acetic acid, because you have the same number of moles of each. They have completely neutralized one another. They are gone. However, you must consider your products. Anything that affects pH must be included as part of the Bca chart. We can cross off water because it doesn't affect pH. It's important for our pH calculations. Everything's based on water, but the water itself, so we generate a few moles of tiny portions of moles of water. That's not going to affect the pH. But the sodium acetate, it absolutely will. Remember, this is a weak base. It is the conjugate base of a weak acid. Therefore, it absolutely has an effect on pH, and we have to figure out how much of it we have. So I'm starting with 0 moles of my sodium acetate. Right before you do the neutralization reaction, you don't have any moles of that thing. The change is based on these changes, the fact that it's in a 1-to-1-to-1 relationship, that this will go up by 0.005, therefore generating 0.005 moles of the weak base. That's your Bca chart. Now the reason that I'm doing this is so that you can understand what's happening in your flask. Used up, gone, not there, generated. So what is in your flask at the equivalence point? No sodium hydroxide or acetic acid, but you've made 0.005 moles of the sodium acetate. Therefore, the pH is going to be based on that number, that 0.005 moles right there. The pH will absolutely be based on how much, on that amount and calculations that we do with that. Now, that thing right there is a weak base. So it's not a strong base. So we have to do an equilibrium calculation in order to calculate pH. Realistically, this is part 1. Part 2 is equilibrium. We cannot, however, use the Henderson-Hasselbalch equation because we do not have a buffer. The only thing we have is the weak base. We do not have any weak acid. We used all of it up. You cannot use the Henderson-Hasselbalch equation to solve for pH here. You are missing one of the major components necessary. So instead, we have to do a more typical equilibrium problem, where you write a reaction, you fill in an ice chart, and then you go to the expression. You have to. You don't have an option. There is no buffer. There is no shortcut. So for the part 2, for the equilibrium problem, what do we have in our solution? We have 0.005 moles, and I'm going to write this as the base of the base. OAC minus, the acetate ion. That's the thing that's impacting the pH, right? It's coming from the sodium acetate. So we can start by recalculate molarity, because we're going to need that. So I'm going to take my 0.005 moles of the acetate, and divide that by the total volume. This is just like before. So I've got 0.05 liters from the sodium hydroxide and 0.05 liters from the acetic acid. Remember, this is total volume. And when we do this, we get a molarity for the acetate ion of 0.05. That's a base. This guides us for the rest. That fact will guide us for the rest of the problem. We have in our flask, what's in the flask? 0.05 molar acetate ion. That is a weak base. So we want to write a base dissociation reaction. Getting started, right? So we want to say OAC minus. Write a base dissociation reaction. How do we do that? Add water, necessary when writing a base dissociation reaction. What will it make? What do bases do? They accept protons. So what is this base going to accept a proton from? The water. This is going to generate hydroxide and some acetic acid. We're going to fill in an ice chart, right? We have a base, so we wrote a Kb reaction. If you had an acid, you'd write a Ka reaction. If you had an insoluble salt, you'd write a KSP reaction. We have a base, so we're going to write the base dissociation reaction in order to figure out pH. Ice chart. Step 2, the 3 steps in solving the equilibrium problem. Filling in molarity. Okay, so what's the molarity of the acetate ion? I already calculated that. That's 0.05 molar. Cross off the water because it doesn't enter into the equilibrium expression. Initial concentrations, 0 and 0. This has become like a KB problem from the homework. You are now saying, now that this is not the same acetic acid as before. This is the acetic acid that you get from the acetate ion dissociating. This is a very different acetic acid. That's why we're seeing it's starting at 0. Because we used up all of that initial acetic acid that we had to begin with at the beginning of the problem to neutralize all of the sodium hydroxide. So this is a new acetic acid. This is the acetic acid that comes directly from the acetate ion. Change. Minus X, plus X, plus X. Acetate ion concentration, 0.5 minus X, approximately 0.05, X and X. Now we're going to go to the expression. This is a base, so this is Kb. Writing the expression. That's the expression. Now, at this point, hopefully you might be noticing that the problem does not give you the Kb for acetic acid. Instead, it gives you Ka. This is the point that I will now remind you that way back at the beginning of equilibrium, I said that you might get a problem where you realize you need the Kb value, but the question only gives you the Ka value. And how you might come whining and crying to me saying, but it's not the one that I need. I need Kb, and we only have Ka. You have KB. You have it. You just don't know that you have it. You've got to do something to get it, but you have it. Remember, this relationship right here. The Ka value for a weak acid times the Kb value for its conjugate base is equal to the autoionization constant for water, Kw. So we're going to take the Ka for acetic acid, 1.8 times 10 to the minus 5th, multiply it by the Kb value, which is what we need, and set that equal to 1 times 10 to the minus 14th. Yes, we do have Kb. This relationship will give us Kb. I cannot use 1.8 times 10 to the minus 5th here because it's not Kb, it's Ka. It's for the weak acid. We don't have the weak acid, we have the weak base. So, but no biggie, I can use this relationship, which is on our reference table, to figure it out. So, recalculating, or calculating Kb, we get a Kb value of 5.56 times 10 to the minus 10th. And I'm just going to go right ahead and set that equal to my equilibrium expression, which from my ice chart is going to be x squared over 0.05 molar. Right? That's coming right from the ice chart. So now we're just solving for x. Go ahead and solve for x. Get a value of 5.27 times 10 to the minus 6. Remember, this question is looking for pH. So if you go back and look at the ice chart, what does x represent? X represents the hydroxide concentration. X is the hydroxide concentration. We can absolutely use this for pH. I'm going to take the negative log of that to get the pOH, because I think that that's sort of most direct, get a pOH value of 5.28, and pH is simply 14 minus pOH, so I'm just going to do 14 minus 5.28, get a pH value of 8.72. And we do want to do our check. Let's see, our X value is 5.27 times 10 to the minus 6. We compared that to 0.05 molar. We want to make sure that that's less than 5%. That is approximately 0.01%, so that is significantly less than 5, so we are good. So the big point about this type of question is that if you are at the equivalence point, so this is part C, if you are at the equivalence point, you have to think about how much of that weak base, in this case the weak base, you have generated after you neutralized all of your weak acid with all of the strong base, that original Bca chart, that sodium hydroxide plus the acetic acid. You use both of them up, great, they're gone. But you have created something that absolutely has an impact on the pH of the solution in creating that sodium acetate. So this whole second part that we did was simply an equilibrium problem using that sodium acetate, using that acetate ion that was created and calculating pH based on that. Where students tend to run amok, honestly, couple areas. First of all, this right here, forgetting this. That's huge. If I give you Ka, you also have Kb. If you need Kb, as we did in this case, no big whoop, take Ka and get Kb. The second area where students tend to get confused, it's in writing the reactions. It's in thinking to write a base dissociation reaction for the equilibrium part here. They can usually get the neutralization reaction just fine. It's neutralization. You know how to write a neutralization reaction. You've been doing that since Regents chemistry. But then it's realizing what they need to do for the second part of the problem. The second part of the problem is simply, all it is, simply an equilibrium problem. And equilibrium problems have 3 steps. Reaction, ice chart, expression. The reaction that you write is based on what you have. We had a base. That was it. That was the only thing left in solution. So we're going to write a reaction for base dissociation. That's what we do. Those are really the big places where students tend to mess up. I have a feeling that with this class in particular, we're actually pretty good at remembering the total volume, that when we recalculate the molarity, we have to take that into account, but that's been a problem in the past. So just sort of letting you know there. That's why, as you can see, I mean, this is, I'm at 15 minutes. We've got 3 questions, part A, B, and C, 3 questions, and it can be a lot of work because these are multiple part problems. You've got to do Bca chart for part 1, and then an equilibrium problem for part 2. It really uses everything that we've done, everything that we've talked about. It's putting multiple things together. That's why this is a secondary topic. But I'll add also, it's a secondary topic. It's not a primary topic. So don't panic too much if you think that you're going to have a ton of problems with this, because you have to make sure you master the primary topics and make sure those are really under your belt.